This is in part to introduce why we need limits, and it's also going to introduce limits, but I'm going to talk about it in the context of rate of change of functions. And really there's two big questions in calculus. It's not confined to that, obviously, but two of the most important questions in calculus is how fast when you're talking about things, and then also how much when you're talking about things. So if you're thinking about maybe driving in a car, you know, how fast you go and how far you go are two of the questions that that you are likely to ask yourself. And if you know the distance and how that changes with time, you'll know it's the change in velocity. If you know how fast you're going for how long, you'll know how far you're going. And so calculus gives us the tools to look at these kinds of things with functions that vary over time and not just a constant rate of motion. So let's look at this little line segment here, and the slope m represents the rate of change, right? It's when we go from x1 to x2, and from the function takes us from y1 to y2. So if we use this definition, we'll get the rate of change. So the slope of a line, if this is a distance function, the slope of the line would be the speed, right? And so if we, I'm going to look to change some of the variables here, and I'm not really changing any of the definitions. I'm just changing how I'm stating this. If instead of y I call this a function of x, so I have f at x2 and f at x1, my definition changes to that. And then I'm going to talk about this change in x as delta x, and that means x2 minus x1. Delta is the Greek letter for d, and we just use that to indicate small differences in calculus. So I can say x2 is going to be x1 plus delta x. That's one way to look at it. Or I can say delta x is just the difference between x1 and x2. So why would you do that? One of the things that we're going to do is we're going to start looking at just a point and how the graph behaves around this particular point. So we're going to use delta x and almost exclusively, and we're going to kind of ignore the x2, even though we still mean x2, but we're going to refer to it as x1 plus delta x. So it's, you know, maybe a time at 2 minutes plus 30 seconds or something of that sort. So if I take this, the green definition of my slope here, and I put in this x2 minus x1, what I'm going to get is, instead of x2 here, I'm going to have x sub 1 plus delta x, and then x2 minus x1 is delta x. So this here is exactly this equation, just with different symbols in it. Okay, I'm using it as a function, and there's no x2 in here. It's always x1 and delta x. Okay, everybody follow so far? The symbols hopefully aren't too bad. This difference ratio is going to be really important. In fact, you're going to live with this next few weeks. So get used to seeing that particular thing. So I'm going to call that the average rate of change over some increment of x, some delta x. Now, if I look at getting delta x to a really small time, so let's say I'm driving. If I drive over an hour, I say, okay, I'm going to go this distance divided by 1 hour. I can look at my rate of change with shorter periods of time, 30 minutes or 15 minutes or 5 minutes or so. And if I get really, really small, like if I say, what is my average rate of change over 1 second? You know, in a car you would expect that that's pretty close to being your instantaneous rate of change. So as this difference, as the amount of difference in that denominator goes to 0, I'm going to call this the instantaneous rate of change. Now, my notation here is perhaps new to you. This is, the way we read this is the limit as delta x goes to 0. Now remember, we used that arrow before when we were looking at long and short-term behavior functions. We would say as x goes to 0, f at x would go to infinity. It's kind of the same thing here. What we're doing is we're saying, okay, we're going to have this delta x And we're going to evaluate this thing as x goes to 0. So I'll return to that notion in just a couple minutes, but I want to maybe expand on the instantaneous rate of change just a little bit first. Okay, so the reason why we do this is that we can now move away from what a line is, and we can actually look at functions that are not a line, and we can define some of the behavior. For example, if you have rapid rates of change and slower rates of change depending on what time it is and things of that sort, we'll be able to make actually make functions that are the derivative of our original functions. So let me go over some terms that we're going to add to our vocabulary of the function behavior. So obviously when a function increases, we can say that this is an increasing function. If we say it's strictly increasing, that means that it's always increasing. If we say it's non-decreasing, we're saying it's increasing or it's 0. We'll use this term to describe functions in this way, and also we'll look at functions, let's say within a certain range, that will say that this is an increasing function between the values of x of a and b. Okay, so clearly this function decreases and increases, and we'll say it's increasing over an interval a to b. And we have the same kind of terminology and considerations for decreasing functions. Okay, so nothing revolutionary there. It's just a matter of assigning some ordinary English words to some mathematical concepts that we'll be using. Okay, when we talk about functions, so here's just an arbitrary function. The maximum of this function might go off to infinity, and the minimum may go off to negative infinity, but we have these peaks and valleys. It's kind of like in a mountain range. We can talk about local peaks. The Mount Diablo is a peak. It's not the tallest peak in California. That's Mount Whitney. But we can talk about local maximums and local minimums. So we're talking about these times where it reaches a certain value and then turns around, and here it's decreasing and then it starts to increase. Here it's increasing and then it starts to decrease. So we call these local maximums and minimums. Now the word local is kind of subjective. That we can say, well, clearly within this range, that's the local maximum. Okay, there's no precise definition that it has to be within a certain percentage or whatever. Yes?
Is that the same as the relative minimum maximum? The relative minimum maximum?
Yeah, yeah. Yeah, you hear that term as well, the relative min and the relative max. Okay? And in fact, I'll probably use those interchangeably now that you say that, but that's true. Okay, so when we talk about local mins and maxes, we're talking about local extrema. So when we say local extrema, we're talking about both the peaks and the valleys of it. So extrema is just kind of the generic max or min. Now, we can talk about these curves as being concave curves. We never talk about necessarily convex curves. We always refer to the concavity of a curve. We're going to call this concave up, and we'll call this concave down. And the way to remember that is think about the palm. Your hand, well, some people can bend their fingers back, but generally your hand just bends one way. And so when I have palms up and I curve my hand, that's concave up. And then concave down is when I turn my hand like this. Okay, so that's easy to remember. It's the palm side is the concave side, so this is concave up and concave down. So every curve that changes like this is going to be either concave up or concave down, or you might have a straight line. That's where you don't have any concavity. But where it's curving, you'll have a particular place where it changes. And we call that an inflection point. That's where the concavity changes. So I'm concave up here, and then all of a sudden I'll go concave down. The point where it makes a transition is called the inflection point. Okay, everybody good with the vocabulary so far? Okay, so think about what concave down means. That means that the rate of change is decreasing. All right, that doesn't necessarily mean that you're decreasing. For example, this is concave down on this side. The function is increasing, but the rate of change is slowing down. So with concave down, the rate of change is decreasing. So here we're talking about the rate of change of the rate of change of the function, right? So here we have an increasing function, but it's not increasing by as much anymore as x increases. All right, so we have to think kind of in terms of two rates of change now. And then also concave up, what means is that the rate of change is increasing. Okay, so here my rate of change is decreasing, but it's at an increasing amount. Okay, so my function is decreasing, but since the decrease is slowing down, that means I'm speeding up. Think about what this is like if you're driving in a car, and let's say this is your distance, okay? When you're moving forward, you're increasing your distance, but if you don't change your distance very much anymore, you're kind of slowing down. So even though you're driving forward, it's possible to still be moving forward and slowing down. So, you know, we usually talk about this as acceleration, right? If you're accelerating, that means the rate of change is increasing. When you're decelerating, you're putting on the brakes, that means the rate of change is decreasing. When you put on the brakes, you don't automatically go backwards. You're still going forwards, but your rate of change is going at a slower rate. Okay, so this is kind of an important thing to think about with increasing and decreasing functions and concavity. So when your minds are idle, not that they're idle much, but when your minds are idle, think about this, because it's something that I think over the next few weeks is going to be important for you to process, so you don't have to kind of scratch your head, and if you're answering a question that you have to kind of rethink the story all over. Think about concavity going up means that the rate of change is increasing. Concavity down means the rate of change is decreasing. You had a question there?
The question doesn't really make sense anymore to me. Like I was saying, what if you're accelerating slower than you're decelerating? Does that mean the rate of change is going up?
Well, you're either accelerating or decelerating. You're not doing both.
Yeah, but okay. All right.
Okay? Okay, so let's go back to limits now. Here's the general way to write it. This is the limit of x as x goes, the limit of f at x as x goes to c. Or you can read it, the limit as x goes to c of f at x. Okay, there's two ways to read it. But basically we're looking at what does this value ultimately head towards as x goes to c. Okay? Okay, now sometimes this is really easy. The limit as x goes to 2 of the expression x plus 3. What is this expression going to as x gets really close to 2? Well, this is getting really close to 5. And so what we say is that ultimately that this thing will equal 5. Now notice, though, that I don't ever get to 2 on this. This is as x heads to 2. We're going to have an exception where we don't mean that x will ever be 2. Now there's some cases that, like this one, is really easy to evaluate because we can just stick a 2 in here and say 2 plus 3 is 5. But the limit notion means that we're getting arbitrarily close to 2, not equal to 2. So in other words, I could be a billionth off of 2, or I can be, you know, any arbitrary distance. Now, that second section in the text that deals with the delta epsilon definition addresses this, where your delta is how far away from, or your epsilon is how far away from this function are you from 5, and your delta is how close does x have to be to 2 in order for that function to be an epsilon away from 5. So the notion of a limit is very old. The delta epsilon definition of a limit, which is the formal limit that we use in calculus, is not as old as the notion of a limit. In fact, that was one of the big problems in defining calculus formally, is that there was no way to formally define what a limit was, and that delta epsilon thing is the formal definition of it. Okay, sometimes this is easy, sometimes this is hard though. Okay, so let's say our function f at x equals 2x. Now here's my instantaneous rate of change, right? I mean, this is by my definition, the instantaneous rate of change. You know what the instantaneous rate of change of 2x is, right? It's just a slope, it's 2. But if I plug these numbers in, I'll get 0 over 0. As delta x goes to 0, this becomes 0 down here. And as delta x goes to 0, this becomes just 2x minus 2x. So you see 0 over 0. But you know what the answer is? The answer is 2. So how do we get that? And that's part of what we're going to learn in terms of evaluating limits, is that we're going to figure out how do we determine this without really even knowing what the answer is yet. So we're going to get these indeterminate forms of 0 over 0, and we'll figure out how to do that. Okay, everybody with me? Do you see the difficulty with this one? I mean, in the function you should be able to tell the slope is 2. If we put it in our limit definition of instantaneous rate of change, we get 0 over 0. You know what the answer is. This, just plugging it in doesn't work. In this case it works, but not in this case. Okay, so I'm going to have a lot of new terms here. Let me just show the whole slide. On the final exam, I'm going to ask you to give me the limit definition of a derivative, and this is what you're going to show me. Okay, so this is a question that you're going to know well in advance that you'll have to regurgitate. But this is what how we built up figuring out what the slope of the line is. Okay, so what I'm going to call this line, if I take 2 points in a curve and connect them with a line, that line is called a secant. Now you might recognize that as a trigonometric function, and it is, but geometrically what a secant is if you just take a line and put it through 2 points on the curve. So the slope of the secant is just the slope of the definition of line that we had, right? That was f at x2 minus f at x1 over x2 minus x1, and if I put that in the delta form that I had before, I get this. So there's the slope of the secant. So in other words, the secant represents, the slope of the secant represents the average rate of change. So what I'm going to do is I'm going to make this secant now a tangent. And so what I'm going to do is I'm going to move this second point, which is x plus delta 1, I'm going to make delta x, I'm going to make delta x small, so I'm going to drag this point along, and you can see that my slope gets closer and closer to what it would be if I just maybe put a ruler up to that curve. So let's say if my delta x is smaller, what I get then is I get this point, and you can see my secant line now is steeper, but it's also closer to what you would expect to be that slope of the line right at that particular point. And so as delta x goes to 0, what we have is this tangent. Okay, so this definition is the slope of the tangent line, and we're going to say that the tangent line and the curve at this point have the same slope, or the same rate of change, the instantaneous rate of change of the curve. Okay, so this is a very important notion that we're going to define what our secant is, reduce delta x down to the point where that secant is now, the limit of the secant is the tangent, and so we get that slope. Okay, everybody with me? Okay, so go back to the definition of a limit. So I think I've said pretty much this already, but the way we read this is the limit of f at x as x approaches a, it equals L. So we can make the values of f at x as close to L as we like by taking x sufficiently close to a from either direction. All right, so in my example where I had as x goes to 2 and we have x plus 3, the closer and closer we get x to 2, the closer and closer we'll get x plus 3 equals 5. Okay, so we can also talk about, remember when we talked about long-term and short-term behavior, I put a little plus or minus as the superscript to whatever value x was going to. We can do the same thing, and we can say we have a limit as x goes to a from the left, so we're going this way, from the negative side, and then of course we have the same situation where we're coming from the positive side, where it's coming from the right. So think about this as a number line. X is going to a from the right here, and x is going to a from the left here. And so that's what what these one-sided limits are about. And we're going to find these one-sided limits kind of useful because it gives us a tool to evaluate some limits that we couldn't otherwise evaluate. So we're going to say that the limit of f at x is L as x goes to a, if and only if it goes to that value from either direction. Okay, so what this means is no markers. We'll go to the board here. If I'm just looking at the function, not the slope now, if we say this is a, as I go this way, my function approaches that value, and if I go this way to a, my function approaches that value. So this limit only exists when we come from both sides to the same value. Just to show you something that's a little different, if I have a function that does this, okay, so when I'm coming from the positive side, the limit, the one-sided limit is here. When I'm coming from the negative side, the one-sided limit is here. Because they don't equal, the limit at a does not exist. I'll revisit that, but that's just a quick definition of the limits from either side. So let's look at this numerically, what this looks like. Okay, so we have this function, a simple quadratic polynomial, and if I look at x going to 1, if I'm going from the left side towards 1, I can get closer and closer to 1. I can go from the right side and get closer to 1 by descending towards 1. If I fill in those values, you can see I get closer and closer to 2, and here I get closer to 2 as well. This is still a little bit above, that's still a little bit below. And so, from a numerical standpoint, we can make a pretty good guess. It doesn't prove it, but it's a pretty good guess that we say that as x goes to 1, this polynomial, its value goes to 2. Oops, that's a little fast. So evaluating them numerically sometimes is really handy. Like that's essentially what we did when we were looking at rational functions, where we're looking at short-term behavior. Does it go to positive infinity or negative infinity? We were, making some assumptions with numbers and kind of plugging it in to see what direction it'd go. We knew it was going to go to either positive infinity or negative infinity, so we were just interested in the sign. But here's a way that we can do this numerically, and sometimes you have to do it numerically. And so let's take this function. Okay, it's just a simple rational function. And so if we factor this out, we know that we have a domain restriction that x cannot equal -1 because the plus ones cancel. Okay? So then my objective here would be what happens when it goes to -1? What happens? Does it go off to infinity? Does it go off to a particular value? So I'm going to make a table of values that goes to -1 both from the left side and the right side. You see how I'm getting closer from both directions. And so x equals -1 is in between the two. So if I were to graph this function the way I know how now, I say, okay, I have the y-intercept at -1, right? When x is 0, we have 1 over -1, so there's my y-intercept. I have a domain restriction at x does not equal -1. I have an asymptote here at x equals 1, and a horizontal asymptote because of the ratio as y equals 1. Okay, so if I graph my values, or do it the way that you've learned up to the last test, you'll get a graph that looks like this, and it would seem like it would go through this point. You see, like if we were just looking at this without the domain restriction, we would say when x equals -1, this would be 0 over -2, which would be a perfectly good point, but we have that value that's not there. But we can say the limit as f at x goes to -1 is actually 0 then. Okay, so here's a case where we have a definite limit that the function is definitely going there, but the value doesn't exactly exist there, so we can't necessarily plug that in from the first expression. Okay, so if I did this numerically, you can see I can get really close to 0. See here I'm a little bit below 0, and here a little bit above 0. Okay, so I can make this make a pretty good guess that the limit as x goes to -1 of my rational function here is 0. So the function doesn't have to have a value at x equals -1, but it will tend to go to a particular value where you have a hole in it like this. Okay, enough theory for the day, right? Let's make a few rules that we can calculate some limits with. Now you can go through the delta epsilon formulas and figure out all these rules exactly, and in fact that's probably a pretty good exercise if you're studying advanced calculus, but we're just going to kind of wave our arms and convince ourselves that these rules are right, and then we're going to apply them to other functions to see if we can see how many functions we can actually get limits to. So the first one is, or this is my ground rule, that c is a constant and that these limits actually do exist. You have some cases where limits, like I drew on the board, they don't exist. But if these limits exist, we're going to say that we can add two functions and that we can take the limits of these things separately, and we get the same limit. So in other words, if the limit of f at x as x goes to a is a certain value, and then this limit of g at x as x goes to b is this should be a. This is not. Let me see if I corrected that. Yeah, there's a correction I have to make here. This should be a. So as f and g go to their own different limits, we can actually first add the functions and then take the limit. What's most useful, though, is if we have two different functions that's a sum, we can calculate those limits separately. And it works also for negative. So if we take the difference between two functions, we get their difference. Okay, and another rule that will help us is if we have a function that's multiplied by a constant, we can first find the limit of the function and then multiply it by the constant. Okay, so think of our example like the the x plus 3 as x goes to 2. If we multiply that whole thing by 2, we can take the 5 times 2 and say, okay, that's going to be a limit of 10. We don't have to do 2x plus 6 and calculate that separately. Same thing goes for product. If we have two limits that go to a certain value, we can make the product of those two and get to the same limiting value. And then it works with the ratios too, with the proviso that the limit as x goes to a of g at x is not 0. Otherwise, we have division by 0, and this whole thing is off. Okay, so this just basically says we can add limits, we can multiply our functions by a constant, we can multiply and divide functions to calculate limits. So that way, if we have a rule, let's say, to calculate what the limit is of f, or of, let's say, f at x equals x, then we'll have a rule that says what the limit of g at x equals 2x equal, because that's just a constant multiplying. Okay. I know it's a lot of writing. I will have it posted, okay? Okay, a few more rules. If we're looking at a limit of a function that's taken to a power, we can first find the limit of that function and then take it to a power. So now if we have the limit of, let's say the function is just x, to calculate x squared, all we have to do is figure out what the limit of x is and then square it. Okay, so it gives us the ability now to work with powers. And this is derived just off of the fact that we're multiplying functions with each other. Okay, so here's some tangible ones. The limit as x goes to a of c is just c, right? If c is a constant, let me put an example around that. The limit as x goes to 3 of 2 is 2. 2 doesn't change because x changes. Okay, so that one's hopefully pretty straightforward. If I'm going to make x go to a, that means x is going to go to a, right? So if my function is f at x equals x, as x goes to 3, f at x is going to go to 3. Okay, so this is just a constant here. And then by this one here, that if I take it to a power, I can take it to that number to a power. So for example, as x goes to, let's say, 2, then 2 to the n is going, we're just going to get our limit by essentially substitution. Now, if we combine all these things, we also get the roots. That if we have something in a root, we can do this by substitution as well. So what this really means is that I can find my limit first and then take the root. Oh, excuse me. Okay, so combining all these rules, I can find the limits of a polynomial and rational functions simply by substitution. Okay, so if we want to know how does x squared plus 2x plus 1 behave as x goes to 4, short story is with all these rules we can just plug it in. So let me take you through a couple examples here. And this is going to be an excruciating detail. I'm not going to make you do all these steps, but I'm going to show you that you have to, formally you have to apply each rule. Okay, so here's my polynomial, x squared plus 2x plus 1 as x goes to 2. The way you're going to do it is you're going to figure out 2 squared is 4, plus 2 times 2 is 4, so that's 8, plus 1 is 9. So the limit as x goes to 2 of this polynomial is 9. Okay, very straightforward. But where this comes from is the fact that I can take, this is a sum of functions, and so I take the limit of each of those separately. Since this is squared, I can put the squared on the outside. This is a constant, I can put that on the outside. And then I know my limit as x goes to 2 of x is going to be 2, so I take 2 squared, and then this is 2 times 2 again, plus 1, and so we get 9. So that's the application of the rules. You're never going to have to do it to that kind of excruciating detail, but the rules that I laid out for you, that's what leads us to being able to do this with polynomials. we're going to find that all continuous functions, we can just plug it in. Okay, but that we haven't gotten there yet. But with a polynomial, that's all we do. Okay, so there's my rule. Now, this is crucial. A is in the domain of f. So when I'm looking at a rational function, remember that I can only plug it in if it's in the domain. So I don't ever want to get into a situation where I have, let's say, some expression over x minus 2, and I'm going, as x goes to 2, that's going to be something over 0. So it doesn't work in that case because 2 isn't in the domain. But where it's in the domain, this rule applies. So that's it. Just plug it in. Okay. Giving up on note taking because I'm writing so fast, right? That's okay. I mean, this I understand. All right. They will be posted, and that's why in part I post the notes, is because I know that these things go pretty fast. So here's a little rule that's going to help us get around things. Okay. If f at x equals g at x when x does not equal a, then the limit of f at x as x goes to a equals the limit of g at x as that goes to a. So think about what this is really saying, okay? This rule is going to get us away from the notion that we always calculate with something that's in the domain. Okay, so let's say A is in the domain of G, or of F, but not of G. If everywhere else they're the same, I can treat one as the other. And you're probably thinking, what is he getting at? So here's an example. So I want to find the limit. So the first thing I do is I plug it in. I get 1 minus 1 over 1 minus 1. I get 0 over 0. Doesn't work, right? So my plug-in rule doesn't work. But what I can notice is that if I'm going to say, okay, so that's not in the domain. If I simplify this by canceling, okay, remember, these functions are only equal if I exclude -1 in the domain. But I can just make my function g at x. Now this has -1 in the domain. So now what I can do is say, okay, these two functions, f and g, so long as I stay away from -1, are exactly the same, right? Anything I put in g, I'll get the same result for f. This domain restriction exists with f, but not with g. And what I'm saying with this rule is that the limits are going to be the same. Okay, so my limit is actually 1/2. So let's see what's going on here. I don't have a marker. Let's graph this. Let's graph f and see what's going to happen with it. Actually, let me take g, and g is 1 over x. So basically, that's going to be that's going to have an asymptote at -1, and then it's going to look like my toolkit function 1 over x, like this, right? And the place that I'm interested in, if I look at this function, since I have this x minus 1 over x minus 1, that causes a hole at x equals 1. So where we have 1 here, if I were to properly graph that, this would be f at x with that hole. So what I'm saying with using, I should maybe use a different color, but if g at x doesn't have the hole and f at x has the hole, I'm saying that the limit as x goes to 1 is the same for both functions. So f at x, if I'm interested, where is this going to as I go closer and closer to 1? It's going to go to 1/2, is I could evaluate that with g at x, which doesn't have the whole. Okay, does that make sense? So in other words, it's a way to deal with these kinds of domain restrictions and figure out, it may be useful. You know, what is that value? What is the function value if it were to exist then? Okay, so let's look at one of these now that my function is going to be x squared, and as h goes to 0, what does this function equal? Now this is the this difference ratio. Remember, we define this as the rate of change of our function at this value, at 2. So if I make my graph, you all know what a parabola looks like. What I'm really asking is, what is the slope of this function when x equals 0? Or not when x equals 0, when x equals 2, right? It's f at 2. So you can see with our, if I make a quick sketch of this, and this is, of course, 4, what I'm looking for is, what's the slope of that tangent line? Now, if I just plug in a 0 here, I get 0, so I get f at 2 minus f at 2 over 0, so I get 0 over 0. Not very helpful. Almost every one that we do that we're trying to calculate a rate of change of a function is going to end up to be 0 over 0. So we have to have a different treatment of it. So what I'm going to do is I'm going to actually expand this. I'm going to plug in my function. I'm going to expand this now. So this is 4 plus 4h plus 8x squared minus 4 over h. And then my 4 and negative 4 cancel out, so I get 4h plus h squared over h. And here, if I divide by h, I get, this just becomes 4 plus h. Now here I have a function, a simplified function. As h goes to 0, what's the limit? It's easy. It's 4, right? As h goes to 0, my function is now 4. So I can write, oops, that was way too fast. So this limit here is 4 because I've just manipulated it to do some canceling. If I were to strictly follow my rules on function, on domain restrictions, when I do this division, I would have to report that h cannot equal 0. But because of that rule that I said with f and g, that if they're the same everywhere else except perhaps that one point, the limits are going to be equal. And we're not actually trying to find the value of this, we're trying to find the limit of it. Okay, the value doesn't exist, but the limit does. Okay, so let's look at this. So what does this represent, really? If I were to take my function as this, f at x equals the square root of x. Okay, and so what I want to do is I want to take f at 1 is going to be this, f at 1 plus h is going to be 1 plus h. And now what I'm actually doing is I'm trying to find the slope of this function when x equals 1. Okay, so the slope of f at x equals x when x equals 1. So this is really what I'm getting at here. And I just want to show you, some of the algebra that you'll have to go through to get to that. So how do you simplify that? Anybody have any ideas? You did a few of these on Friday, I think, didn't you? Yes. Okay, what's your idea?
Equal the numerator to 0 and the sum.
Equal the what?
0 and the sum.
Well, if you put this 0, you have square root of 1 minus 1 is 0 over 0 then, right? So there's no real substitution that we can do here. So we need to change the form. Anybody have any idea? How do we deal with something, how do we get a variable outside of the square root? Yes?
So is it like square root 1 plus h? So you multiply like square root of 1 plus h plus 1?
Yeah, and that's called the conjugate, right? So what we're going to do is we're going to say, I'm going to multiply this by 1 plus h plus 1. And, you know, this is 1, right? So what I'm going to get out of that is I get the difference of the squares over this. So when I simplify this now, this is going to be 1 plus h minus 1. That's going to just be h, and then I have this mess in the denominator. But notice I'm not subtracting anything. So this is good news, because if I now cancel my h's here, I get this function here. And so if I plug in a 0 here, I get 1 over the square root of 1 plus 1. So this is going to be 1/2. So if I look at my, my square root function, which looks like this, okay, and where x equals 1, I'm looking for the slope of this, and what I've just found is that that's going to be 1/2. All right? So this is multiplying by the conjugate. So when you get these square roots, think conjugate, right? Difference between two things, to get rid of the square root, you can make it the difference of the squares by its conjugate. Yes? No? Okay. So a limit only exists if and only if these things are true. Now, let me talk about if and only if. It's not, that's different than just if. If and only if means that if this is true, that's true, and if this is true, that's true. So it goes both ways. It's a if-then working both ways. Think about it logically, like if I said, if I'm in Paris, then I'm in France. That's true. But if I'm in France, then I'm in Paris. That's not true. So that if only works one direction. Okay, so if this one works in both directions. So if this is true, that's true as well. Okay, so let's look at this. The absolute value function is this piecewise function. And so we want to find the limit as this goes to 0. So what do you suppose that is? If I take the limit of the absolute value as x comes from the negative side, it's going to make it negative x, right? And so I can figure out, okay, the limit of negative x as x goes to 0 is 0. Now, if I'm coming from the positive side, the absolute value does nothing, and so it's the limit as x goes to 0 of just x. Notice these are two different functions here, but they both go to 0, so we can safely say that as x goes to 0, the absolute value of x goes to 0 as well. And you can visualize that with the function. Remember how this looks. It's this kind of V-shaped thing. And so when I'm coming down to here, from this side, I'm going to 0. When I'm going up from this side, I'm going to 0. So my limit is 0. And I'm not going to introduce this one. Okay.